Hi, I'm Daniel Mox, and this is our work Opportunistic Communication in Robot Teams. The promise of multi-robot systems is they can complete tasks quicker and more efficiently than a single robot. These performance gains are realized when the robots can communicate and coordinate their actions. While this is easy in tightly controlled spaces, robots are increasingly operating in more challenging environments, which gives rise to the problem of how to coordinate beyond existing communication infrastructure. The solution pursued widely within the robotics community is to form ad hoc or peer-to-peer networks in order to communicate. The principal challenge in this scenario is that actions taken to accomplish the task often conflict with maintaining communication links necessary for coordination. Instead of adding communication constraints to the planning process, we consider the problem of controlling a different team whose job is to ensure reliable communication to the task robots as they go about their mission. This work focuses on controlling these network robots. This problem has been studied widely in the robotics community, with some solutions driving robots to maintain the connectivity of a communication graph, minimize end-to-end bit error rate, or solve flow-based optimization problems. These works use heuristics for communication of varying complexity in their formulations, which may not lead to better network performance in practice. In addition, few works can run in real time, and almost none have been tested on physical robot teams performing complex tasks. In this work, we introduce a new system for communication support. Like other works, we use a channel model for predicting links between robots. However, instead of pairing it with a heuristic for network performance, we instead directly consider the performance of the underlying routing protocol responsible for communication. Using this approach, we formulate a controller that drives robots in order to directly optimize the transmission of packets over the network. We build our system on an opportunistic routing protocol, which is well suited for the dynamic, lossy, peer-to-peer networks robot teams tend to form. It is best illustrated by this example where A wants to transmit to D. Instead of choosing a single next hop to relay, A chooses both B and C as candidates and broadcasts its message. B and C coordinate amongst themselves in an efficient distributed manner depending on who receives the message. If C does not get the message, B can pass it along to D and vice versa, making it less likely A has to retry sending. Using this information, we can enumerate the possible routes a packet could take through the network. We then use a simple linear channel model to compute the probability the packet gets successfully delivered. This formulation emits a gradient-based local controller that adjusts robot positions in order to maximize the probability that the packet gets delivered. In this simple line scenario and channel model, we can compute global optima by exhaustive search and gain insight into the kinds of configurations the local controller might converge to. When the distance between sender and receiver is small, our approach stations both communication robots in the middle acting as redundant relays as shown on the left and middle. Predictably, as the distance grows, they form a daisy chain as shown on the right. We conducted several experiments using a set of 6 scarab robots, each running a full autonomy stack on board with navigation and obstacle avoidance. We also implemented a popular opportunistic routing protocol SOAR in Linux and used it to pipe arbitrary ROS traffic over an ad hoc network. In the first experiment, Task Robot 46 transmits critical status information to its 2 task teammates in a situational awareness mission. At first, we don't use communication support, and these task robots must transmit directly with each other. Bright red lines show strong communication links, and faint lines show weak ones. Predictably, as the task robots reach their stations, the direct links from 46 to the rest of the team waver. Over the course of this experiment, the flow of critical mission information ceases as the robots move far away from one another. Next, we ran the same experiment with communication support from robots 40, 41, and 45 running our controller. While initially clustered together, providing relay redundancy, they spread out to form a communication web as the task agents grow further apart. Unsurprisingly, with communication support, the link between task agents is maintained more reliably over the duration of the mission. Finally, we showed our system providing communication support during multi-robot exploration. Agents 42, 44, and 46 seek to efficiently explore an area by coordinating their actions, and Agents 40, 41, and 45 serve as communication support running our controller. Blue squares represent new frontiers, and red squares represent visited ones. As they explore, the task agents constantly update each other, maintaining a shared list of frontiers, which enables them to travel to different areas. The communication robots constantly adjust their position to maximize the performance of the network and ensure the task agents can effectively coordinate. In the end, our communication support system enabled the task robots to reliably coordinate their actions and efficiently explore separate areas of the space. Thank you for watching, and we hope you check out our paper to learn more.